Students, Jai Swaminarayan. This is Professor Urvish Mewada, Head of the Department in the Electrical Engineering Department. I am the subject matter of Power System 2, which is in the 5th semester Electrical Engineering, and GTU subject code of this subject is 3150911. Students, in last lecture of chapter number 3, means lecture number 2, we studied about the examples based on the short transmission line. Now for this chapter, the topic number 4 is medium transmission line. Now the subtopic of this topic number 4 is medium transmission line. So sorry, uh, as we know that the length and voltage of the line increases, uh, the capacitance gradually becomes of greater. Why this capacitance is increases? Imagine that we are talking about transmission, means we have two transmission poles. In between we have the three transmission lines, say RYB. Now imagine it is a structure like a capacitor. Why it is a structure like a capacitor? Because imagine that between two conductors we have air as a medium, means we have the two conductor, in between we have the air, so it is a like construction of the capacitor. So we are imagining over here that line capacitance between two lines. So that's why if the length of the two line will increase, so as the capacitance between the two lines will increase. How this capacitance between two lines are increasing? The capacitance of the capacitor basically depends upon the area of the plate. So here we are considering transmission line as a plate. So between two transmission lines we have the air as a medium, so we are considering this as a capacitor. So as length of the line is increases, that's why the capacitors, here we are considering that capacitors plate area is also increases. So as the capacitors plate area is increases, capacitance will increase. So that's why for the medium transmission lines we are considering capacitance effect. In previous case, for the short transmission line we were not considered the capacitance effect, because the distance between two pole is short compared to the long medium transmission line, because here the distance between two pole is increases. So as the length of the conductor will increase, so as the capacitance between two uh, wires will increases. So that's why we are considering capacitance effect over here. Now since the medium transmission line has the length that we already know, we discussed in the previous lecture that the if the length of the say transmission line increases above 50 kilometer, means 50 to 150 kilometers, then this transmission lines indicated as a medium transmission line, and the transmission voltage is also greater than the 20 kV. So the effect of the capacitance cannot be neglected, because the here we are here we have the voltage, that is transmission voltage in the previous case was below 20 kV, and in the medium transmission line we have the no, transmission voltage, say above 20 kV, and the line length is also increased, that is 50 to 150 kilometers. So that's why we are considering the capacitance effect over here. So from that, in order to obtain the reasonable accuracy in medium transmission line calculation, the capacitance must be taken in the consideration, because as the line length is increases, the capacitance between two lines, means the imaginary capacitance created between two lines will increase, because the line length is increased, so as the it is proportional to the line length is proportional to the capacitance. So as the line length increases, the capacitance between two conductor, imaginary capacitance between two conductor will increases. So that's why one thing is we have the more transmission voltage, and we have the length of the, means more transmission line length. That's why from that we can say that the capacitance between two conductors, means the capacitance which forms between two conductors will increases because the length of the line is now 50 to 150 kilometer. So uh, uh, so that's why in order to make the calculation simple, the line capacitance is assumed to be lumped, means it is connected or concentrated in the form of capacitor shunted, means we are considering capacitance effect between two lines. That's why it is called shunt capacitance. So it is shunted across the line at one or more points, means we are considering means capacitance effect between two conductors, means in the vacant space between two conductor. So that's why we consider that capacitance between two lines is in parallel, means it is shunted, and we are considering we are taking means random points in the calculation while we select the capacitance of the transmission line. Means imagine that we have the two transmission line like this, and here we have the two poles. So we can consider means capacitance any of the point between transmission lines. So say we can consider at the middle, or we can say we consider at the end of the transmission lines. So this treatment of localizing the line capacitance gives the reasonable accuracy or accurate result while we analyze the transmission line for the analysis of medium transmission line. So generally, most commonly common methods that we use to determine the capacitance or solve the medium transmission line means it is known as localized capacitance method. So for solution of medium transmission line, we have the three methods. First is end condenser method, second is nominal T method, and third one is nominal pi method. Since the above methods are used for obtaining the performance calculation of medium transmission line, so they can also be used for short lines if their line capacitance is given in the particular problem. With the help of the medium transmission line analysis formulas, we can solve the short transmission line also. But if it is necessary to calculate the capacitance between the conductor, means imaginary capacitance between the conductors, then we can apply this method for the for the short transmission lines also. So from this we can say that if the line length will increase, so as the imaginary capacitors area of the plate will increase, so as the capacitance will increase. And if the input voltage is more than the charging effect between two conductor will be more. So that's why for the medium transmission line, the voltage of the line say increased above 20 kV. So that's why we are considering imaginary capacitance, and we are considering one or two or more than 2 points of the capacitor for the analysis of this medium transmission line. Let's see how it can be analyzed. Now the subtopic of this topic number 1 is end condenser method. So in from this diagram you can see that end condenser method. So here we are considering one transmission line having resistance R and its inductive reactance XL. As we already know that we indicate the transmission line as R plus jx. So this is the transmission line at which at the end of the transmission line we consider the effect of capacitor over here, and this is the load which is connected at the end of the transmission line. So that's why this as we drawn the capacitor over here, it means it is the end condenser method. Means capacitance effect we have considered at the end of the transmission line. That's why it is called the AND condenser method. So and also we have considered that the capacitance of the line is lumped or concentrated at the receiving end. Means this end is also called a receiving end. Means we are transmitting the power from this side, that's why this is called sending end side, and this is the load side, means it is the receiving end side, that's why it is called receiving end or load end. So this method of localizing the line capacitance at the load and overestimates the effect of the capacitance. We considered the effect of the capacitor at the end of the transmission line or at the receiving end, that's why it is called the AND condenser method. In the diagram, one phase of the three phase transmission line is shown, means this is one phase of the three transmission line. So it is more convenient to work uh, in phase, means in the phase instead of the line to line values. So here we are considering the effect between line to neutral. So let the current IR is the load current per phase. These are the means the terms which we used in this method. Now R is the resistance per phase of the transmission line. XL is the inductive reactance of the transmission lines, means it is the per phase inductive reactance of the transmission line. Now C is the capacitance per phase, which is the which created between the phase and neutral. And the cos phi r is the receiving and power factor, means always it is lagging because we are not using any means capacitive circuit, because this is the imaginary capacitance which is created between the transmission lines. And the Vs is the sending end voltage per phase. So the phasor diagram of the circuit that we see over here, that is the VR is taken as a reference because it is at the receiving end, that's why we have drawn the receiving end phasor diagram. So VR is receiving end voltage, and from VR to somewhat angle lagging, say IR, means cos phi r angle, the IR flows. And the IS means sending end current, which is flows somewhat lagging to VS. So when we draw the VR in the direction of IR, the resistive drops will take place, so that's why it is ISR. And at the 90-degree, the inductive reactance, means reactive drops will take place. This is the impedance triangle. So the resultant of this resistance and inductive reactance is the impedance of the circuit. And when we join this point that we get from the impedance triangle and the origin, it is the sending end voltage. And from the sending end voltage, the from phi s degree, means the sending end power factor cos phi s, the phi s degree, the is will take place, and the resultant of this two is the capacitive current IC. Now in the previous slide, uh, taking the receiving end voltage VR as the reference phasor. So here we are considering the effect, that's why the VR is taken as a reference. So from this slide, the means the simplification of this medium transmission line is VR is equal to VR plus J0, because VR is at a reference, that's why there is no angle at VR, so that's why VR plus J0, we are indicated that phasor voltage VR is equal to VR plus J0. Now load current IR, so IR is flowing at phi r degree, so IR has the two components, so IR into cos phi r minus J sin phi r. So from this phasor diagram we can write this equation. Now the capacitive current IC, we are writing this equation. So IC is as we know that V is equal to IR, so VR is equal to I into R, but here we are considering the effect of capacitive reactance, so that's why it is 1 upon XC. So IC will become J into VR omega C, where omega is the 2 pi f, so that's why J 2 pi FC into VR. Now the sending end current is the phasor sum of load current IR and the capacitive current IC. See, from this you can see that this is the IR and this is the IC, so IS will become the phasor sum of this two, because this is flowing in this direction, so that's why IR plus IC is equal to IS. So from this we can write this equation: IS is equal to IR plus IC, where we are substituting the value of IR. So IR is the IR cos phi R minus J sin phi R, plus IC is equal to J omega C, means 2 pi FC VR. So as we solve this equation, we will get that IR cos phi R plus J minus into the bracket minus IR sin phi R plus 2 pi FC VR. So from this we can write that IS, because this is the resultant of this two, so is into Z. So Z is the impedance of this medium transmission line, so Z can be write as R plus JXL. So the sending end voltage equation will become VS is equal to VR, means VS, this VS is equal to VR plus ISR plus JXL. So this is the terms from which the VS forms. So VS forms with VR, means receiving end voltage, plus the sending end current, which is related to the impedance triangle of this medium transmission line. So this is the sending end voltage equation, and this is the receiving end voltage. So from that we can write the voltage regulation equation. So percentage voltage regulation is equal to sending end voltage minus receiving end voltage divided by receiving end voltage, as we get the value of this VS and VR. So we can find out the voltage regulation from this terms. So the voltage transmission efficiency, as we know that output upon output plus losses, so the power delivered per phase divided by power delivered per phase plus losses. The losses which take place in this circuit is drawn, means it is written in this previous slide, that is VR cos phi R, and means VR IR cos phi R, plus this is the losses I square R, means IS square R. So by putting this values we can find out the voltage transmission efficiency. This method has certain limitations, so let's discuss the limitation of this method. The end condenser method for the solution of medium transmission line is simple to work out the calculation, yet it has the following drawbacks. So the drawbacks are, there is a considerable error about 10%. So whatever the data will get, means whatever the analysis we perform by this method, having an error, say 10% of error will get after the solution in calculation, because the distributed capacitance has been assumed to be lumped or connected. Here we are assuming that it is connected, so this method overestimate the effect of the line capacitance. So that's why there might be means chances of error, means error can occur, and we will get 10% of error after solving this medium transmission, by assuming the capacitor is lumped at the different points of transmission line. See, we are assuming that the here the capacitance can affect, so we cannot predict that that point at which the capacitor forms. So that's why we are assuming that at the end of the end of the transmission line, or at the receiving end of the transmission line, the capacitance is formed, or in the next subsequent method we considered that the capacitor affect at the middle of the transmission line, or and in the next or third method we considered that the capacitor is affected, the capacitor is affecting at the sending end as well as the receiving end. So we are assuming that at this point, suppose capacitor forms, then what will be the effect of that capacitor? So we cannot predict that that the means fixed point, or we cannot see that capacitor's effect, because we are imagining that the capacitor is forming between two lines. So that's why it can generate the 10% of the error after the calculation. So let's see the example related to the end condenser method. So one example is given over here. A medium transmission line is a single phase transmission line, 100 kilometer long. As we know that the line length, say 50 to 150, it is called the medium transmission line. So here 100 kilometer long has the following constants. So the resistance is given 0.25 ohms. The susceptance is given, it is the reciprocal of the reactance. So sort of susceptance is given as the 14 into 10 raised to minus 6 Siemens, and reactance per kilometer is 0.8 ohm, and receiving and line voltage is 66 kV. And assuming that the total capacitance of the line is localized at the receiving end, so we are considering end condenser method, because the capacitor is located at the end of the transmission line. So determine the sending end current, so is, and sending end voltage vs, and regulation vr means percentage voltage regulation. Supply power factor means sending end power factor cos phi s, and the line is delivering 15,000 kilowatt at 0.8 power factor lagging. So draw the phasor diagram of to illustrate the calculations. So the figures that we have, number 1 and 2, that we will discuss one by one. Sorry. So these are the data given. R is given, that is 0.25, so that is 25 ohms. Then XL is the 0.8, so it is 80 ohms. And Y is the 14 into 10 raised to minus 6 into 100, so it is 10 into 10 raised to minus 4 Siemens. And then VR is equal to because this is the length of the line, so that's why we are considering this is the per kilometer. So this is 100 kilometers, that's why it is multiplied with 100. So 25, 0.25 into 100, and XL is 0.8 into 100, so that will become 25 ohm and 80 ohm. Then the total susceptance Y, it is again multiplied with 100, so that will become 100 in 14 into 10 raised to minus 4 Siemens. So receiving end voltage VR, that is given 66 kV. So from the equation of IR, so it is nothing but the VI cos phi. So P is equal to, P is the power that is delivering, say 15 kilowatt. So P, and VR, this is VR IR cos phi R. So we have the value of VR cos phi R and power. So from that we can determine the value of IR. So that is 284 ampere, and cos phi r it is given, that is 0.8. So from the cos phi r we can determine the sin phi r, that is 0.6. Now according to the data given, and as we are using the end condenser method, so that's, this is the diagram for the end condenser method that we already drawn in the theory section of this transmission medium transmission system. So R is the line resistance, and XL is the line reactance, and this is the phasor diagram which is drawn for the medium transmission line. So from this phasor diagram we can determine that the taking receiving end voltage as the reference, because in the theory section we have discussed that we are considering the effect at the receiving end, that's why we are considering VR as at the reference. That's why VR is equal to VR plus J0, and the voltage of the receiving end, that is given 66 kV. So VR will become 66 kV, there is no angle, so that's why it is J0. Now the load current IR is equal to, IR has the two components, IR is equal to IR is equal to IR into cos phi r minus J sin phi r. By placing the value of cos phi r, sin phi r, and the IR, we get the IR 227 minus J 170 ampere. Now the capacitive current that is IC is equal to J y into VR, because this is the susceptance, so V is equal to I by y. So y is the reciprocal of Z, means impedance. So sorry, impedance, sorry, reactance. So that's why on JY, so by placing the value of y and VR, we will get the I, say J92 ampere. So IS is the combination of, from this phasor diagram you can see that it is the combination of IR and IC. So that's why IR plus IC is equal to 227 minus J170 plus J92. So from that we can determine that 227 minus J78. So from that the magnitude of IS is the under root of this values, so 240 ampere. So this is the sending end current of this medium transmission line that we drawn, and the specific data are given, and from that the data we determine the value of sending end current. Now the voltage drops. So voltage drop equation will become like this. Sorry, see, this is the equation. From that we can write that VR plus ISR plus ISXL is equal to VS. So the equation will become voltage drop is equal to IS into Z. So IS is the sending end current into the, see, voltage drop V is equal to, equation is V is equal to IR. So instead of R here we are considering the impedance, so that's why I is the sending end voltage and R is the resistance. So instead of R we are writing the total impedance of the line. So that's why is into the impedance is R plus jXL. So by placing the value of all this we will get this voltage drop, that is 11,915 plus J 16,210. So we have the sending end voltage equation, Vs is equal to VR plus Is into Z. So we have the value of VR and we have the value of Is and Z. So by placing the value we will get that Vs is equal to 77,915 plus J 16,210. So magnitude of Vs will become the under root of this values. So the voltage means sending end voltage is 79,583 volt. So from this values Vs and Vr we can determine the percentage voltage regulation. So we have the value of Vs and Vr. Now we are placing the values of Vs and Vr in this equation. So from that values we can determine the percentage of voltage regulation. So this is the voltage regulation. 20.58% voltages are regulated when it is transferred from the sending end to receiving end, and by considering the effect of capacitance at the end of the transmission line, at the receiving end of the transmission line, or we can say at the load side. So this is the voltage regulation that we get when we transfer the voltage from sending end to receiving end for the medium transmission line. So referring to that, I must matlab first means phase angle between VR and IR is phi 1. So that is phi 1 is equal to tan inverse of minus 78 by 227. So this is the angle, and from the second figure the phase angle between VR and VS is phi 2 is equal to tan inverse of this two values. We have these values. So from that the angle is 11.50. So total angle phi s is equal to the addition of this two, so 18.96 plus 11.50, so that is 30.46 degree. So from that we can determine the value of phi s. So the value of phi s is placed over here in the cos phi s. So cos phi s means cos of 30.46 is 0.86 lagging. So this is how we can determine all the terms related to the medium transmission line. Now after this lecture you have some assignment questions. These are the examples which which are related to the medium transmission line. You can take snap of these two examples, and the question, third assignment question is explain and the and condenser method for the transmission system with suitable derivation and phasor diagram also, and list the limitation of it. So students, if you have any doubt after this lecture, feel free to call me, and we can solve our doubts in the doubt solving session if you have any doubt. So please take the snap of this assignment questions and the related instructions which are written in this. So please follow these instructions carefully. Thank you very much, student. Jai Swaminarayan. So